As you can see, it's quite a long question as written on the page. And as usual, I would recommend that you read through it carefully 2 or 3 times. So pause the video at this point and do that, and then we'll get back to the question. Having looked through the question, you might hopefully feel a little bit less intimidated. You should recognize that this, although it's a long question, or apparently a long question, it's all fairly straightforward. And in fact, because it's a long question, it looks long on the page because the examiners have actually broken the question down for us into lots of fairly short and tractable steps. And generally speaking, that should make it easier for you as the student to follow through this question. But let's see how it goes. On browsing through the question, you need to pick up on a few key terms to make sure you're aware what this question is all about. Here's the first one. The examiner talks about a polynomial. You need to know what a polynomial is, and you need to start thinking about what typical processes are you generally asked to do with polynomials. Well, here's one of the typical processes. You need to be aware of the factor theorem, what that is and how it applies to polynomials. And then moving on to part B of the question, I guess the key phrase, key 2-word phrase here is stationary points. And again, if you're proficient in your understanding of the content of the Unit 1 syllabus, you should know quite a bit about stationary points. Let's take the question step by step as the examiner has broken it down for us. Let's, from this point forward, we'll not look too far ahead. We'll do exactly what the examiner is asking us to do in the order that he or she is asking us to do it. So let's start with part 1 of part A of the question. We need to understand how to apply the factor theorem. To use the factor theorem to show that x plus 3 is a factor of the given polynomial. The given polynomial is clearly a cubic polynomial. That doesn't really matter at this point. So what we need to do is to identify the value of x that makes x plus 3 0. Well, that is, of course, x equals -3. And what do we do with that value? We need to substitute that value into the polynomial function. Okay, so be prepared, even just for 2 marks, to write down what you're doing step by step. So I'm suggesting that you should write down pretty much exactly what I've got on the screen here. Questions which are largely algebraic like this one, it's tempting just to write down a whole bunch of algebra, which on the page will just look like a collection of numbers and symbols, but that doesn't make it very readable. You're going to have to use some key words such as substitute in your formulated answer. Otherwise, it will be very hard for the examiner to follow what you're actually doing. You might be very clear in your own head what you're trying to do, but getting the marks in the exam is all about communicating your understanding to the examiner. Don't think that you can do that without using some words now and again. So if I were to substitute x equals -3 into that polynomial function, I could write it like this. Okay, so you'll see on both the left-hand side and the right-hand side here, I've replaced x with -3. The left-hand side is just the notation, function f evaluated at the x value -3. On the right-hand side, I have substituted -3 into that expression in terms of x. So I've now got a numerical expression which I need to simplify. Of course, I could just type this straight into my calculator. However, lots of students make mistakes at this point, even when they're using the calculator. The examiner has very deliberately given us a negative value of x to substitute into an expression. This should be a fairly straightforward GCSE technique, but at GCSE and even at A-level, lots of students make mistakes when substituting negative numbers into formulas. I would suggest that the way to avoid these mistakes is to write it in the way that I've written it here on the bottom line. Replace x with the numerical value, -3, and put that value in brackets, whether the value is positive or negative. At this point, obviously, if I type in exactly what's on my screen into my calculator, I will get the correct answer. Okay, but I'll do it without a calculator, so to speak. -3 cubed, I know that's -27. -4 times -3 is +12, and the +15 stays on the end. So if I combine those numbers appropriately at the end, -27 plus 12 plus 15 is, not surprisingly, 0. That's the value I was looking for. The factor theorem is all about getting 0 when you substitute a particular numerical value into an expression. So when I get 0, I write something like this, and again I have to use some words. Hence, by the factor theorem, x plus 3 is a factor of f of x. Let's move on to part 2 of part A of the question. I would suggest you do this in the most obvious and straightforward way. They ask me to express f of x in this factorized form. So I will do just that. That step does not require any work at all. They now ask me, and this is where I get my 2 marks, to determine what the values of p and q are. I've got a couple of possible ways of doing that. I'll do the quick and dirty way, which you may like, or you may prefer another way. We'll talk about that in just a second. So carefully working through this, I will replace the left-hand side here with the given cubic polynomial that I'm given in the very top line of the question there. And on the right-hand side, I will expand brackets. Okay, so left-hand side was dead easy. I know that f of x in this question is just shorthand for x cubed minus 4x plus 15. The right-hand side, I had to expand brackets. What I suggest you do is use pause at this point, expand the brackets for yourself and see if you agree with me. If you don't, or if you're not sure about expanding brackets, here's what I would suggest. The method for expanding the 2 pairs of brackets on the right-hand side, I think the simplest, most straightforward method is to use what I would call the box method. Again, no need to hide your working out in a margin of your page or tucked away in a little corner. The examiner would like to see your working out, so don't be afraid to sketch this out. In case you're still not quite getting what I'm talking about when I refer to the box method, I mean this. It's a multiplication grid. I've just put the multiplication symbol top left there to indicate I'm multiplying, and along the top row there I've got the longer of the 2 expressions in brackets, x squared plus px plus q, and I've split that into 3 separate terms. And down the left hand column there I've got the shorter of the 2 expressions in brackets, x plus 3, and I've separated out as x on its own and 3 on its own. Of course, I could have drawn my grid the other way around. Instead of having 2 rows and 3 columns, I could have had 3 rows and 2 columns. Makes no difference. And then carefully, I would multiply out my grid. So in that top left of the 6 empty cells there, x times x squared is x cubed. Moving across, x times px is px squared, x times q is qx. And on the bottom row of empty cells, 3 times x squared is 3x squared, 3 times px is 3px, and 3 times q is 3q. And then the answer to the bracket expansion is the sum of the terms in those 6 white cells. And again, I'll match them up with the answer that I claimed in the line above. There's my x cubed. These 2 terms together both have x squared, so I've got p lots of x squared plus 3 lots of x squared. So I've tidied that up to write it p plus 3x squared. this term and this term both have x to the power 1, so I've got q lots of x plus 3p lots of x, so that's 3p plus qx, and the last term has no x at all, so it's just 3q. So that's the result of my expanding brackets. So on the left hand side I've got a prescribed cubic polynomial expression, and on the right hand side it's also recognizably a cubic expression, but the coefficients contain unspecified unknown quantities p and q. So we need to determine these p and q, and the way to do that is by equating coefficients. So we're comparing the two sides, both the left hand side and the right hand side are cubic polynomials. For them to be equal, corresponding coefficients of equal powers of x must be the same. Starting with the highest power of x, I've got x cubed on the left and I've got x cubed on the right. That matches up, that's good, but it doesn't give me any useful information. Next highest power of x would be x squared. On the left hand side there is no x squared, and on the right hand side I've got positive bracket p plus 3 lots of x squared. Apologies for the crude highlighting there. So if I'm equating coefficients, the coefficient of x squared on the left hand side here is clearly 0, and on the right hand side it's p plus 3. So whatever p is, it must satisfy this little equation, 0 equals p plus 3. Let's go down to the next power of x, that's x to the power 1. Here I've got terms on both sides. On the left hand side I have negative 4x, and on the right hand side I've got positive 3p plus q lots of x. So those two coefficients, the negative 4 on the left and the 3p plus q on the right, must be equal. So that gives me another little relationship involving p and q. And don't forget, I've also got the coefficient of x to the power 0, in other words the term that doesn't show an x. On the left hand side that's positive 15, on the right hand side it's positive 3q. Equating those, I must have 15 equals 3q. So I've actually got 3 relationships for 2 unknowns. Now if you're on the ball you'll think that that's a little bit fishy, and it is in a way, but let's carry on. Let's take those one at a time. The first one, 0 equals p plus 3. I'm sure you're screaming at the screen now because you know what the answer is. That tells me that p must have the value negative 3. Okay, using that I can then solve the next equation for q. If I substitute in p as negative 3, then I'll have negative 4 equals negative 9 plus q. I'm not going to bother to write this out because I think it's a bit basic, but hopefully you want to do this in your head or scribble it out on a bit of paper. You should get q equals 5. Now I've got one more relationship for free, if you like. I've got 15 equals 3q. Now fortunately, or not fortunately, it's for a very good reason, that agrees with what I've just found out about q. Q is 5 and 3 times 5 is 15. So that all ties together. So on the line before the last line here, that's what we call an overspecified problem. I've got 3 equations for 2 unknowns. I don't really need 3 equations. And that's all because we actually used the factor theorem earlier on. Okay, so I've already done a lot of work, which is telling me a lot about the coefficients of how this polynomial factorizes. So just to put this into its final terms, I mean, we found p and we found q. As far as we can tell, we have done what the examiner has asked. But if it were me, I'd sort of meet the examiner more than halfway. I wouldn't just leave it like that. I would write out that full factorization. If you read the wording of the question, part 2, very carefully, the examiner asked me to do this. He or she did not ask me what are the values of p and q. He or she asked me to write it in this form. So if nothing else, do exactly what the examiner is asking you to do. Okay, there shouldn't be any ambiguity in it, really. Okay, and if you sort of see a shortcut, or you think you see a shortcut, there probably isn't a shortcut there. The examiner would like to show all of the explicit detail that he or she is asking for. But at this stage, that should be it. We should have answered part 2 of the question. Part 1 and part 2, we've done all of part A. Let's move on to part B. Just one quick thing before we do go on with part B. It may have occurred to you at this point there is an alternative way of doing part 2 of part A. I could have used polynomial division, in which case I would have divided the cubic polynomial at the top, x cubed minus 4x plus 15, by x plus 3. It's entirely up to you if you want to do it that way. The examiner would be perfectly happy with that. I think the way the question is phrased, I think the more obvious approach is the one that we've used here. Part B seems to be, at first sight, unrelated to part A, or at least part 1 of part B seems to be unrelated to part A. But again, if you've read through the question carefully, you will recognise there's a very close connection between them. So here I'm given a 4th degree polynomial. The other word for that is a quartic polynomial, or a quartic function, if you like. So in the first part of the question, part A, I was dealing with a cubic function. So on the face of it, there's a bit of a disparity there. There doesn't seem to be much of a connection. And secondly, I'm not being asked to factorize it or anything like that. I'm being asked to differentiate it. The examiner does not use the word differentiation. The examiner used the standard symbol for derivative of y with respect to x. And the examiner is expecting me to understand that, and the examiner is expecting me to know how to do this. So again, do exactly what the examiner is asking for. Write down dy by dx equals, then term by term differentiate that 4th degree polynomial. I think this is one of the more straightforward parts of Unit 1. And for those of you who have done Level 2 additional maths, this is probably a bit of a doddle. But in any case, let's do it in really clear step-by-step detail. So first, I'm going to differentiate the x to the power 4 term. So the number 4 comes down in front, and the power decreases by 1. If you're wondering why I've got the brackets there, you're right, I don't need the brackets, but you'll see in the next term why I put the brackets in like that. The next term is negative 8x squared. The negative 8 stays where it is. The 2, which was the power of x, comes down in front, and the power decreases by 1. Hopefully now you can see why I'm putting brackets there. The next term is just a constant times x. Feel free just to quote the rule that the derivative of a constant times x is just that constant. So positive 60 times x differentiates to give positive 60. And the last term is dead easy. Whenever you differentiate a constant, you get 0. I'm sure looking through this, you're looking at the screen and you're thinking, yes, I would have known all of those things. It's remarkable how common certain mistakes are. A common mistake with this type of question is for students to forget to differentiate the plus 7 at the end and to write in their derivative, instead where I've got plus 0, to write plus 7. So they crucially forget to differentiate one of the terms. Now, at this stage, you wouldn't lose many marks for that. You'd obviously lose 1 mark, but it will mess up a later part of the question, and something which is supposed to work out neatly won't work out neatly. Maths, if nothing else, is a progressive subject. Bits of questions are built on other bits of questions. And if you get one thing wrong, it's not the end of the world, but it will lead you down a path that you really don't want to go down. You don't want to be going wrong early on in a question. Okay, let's just tidy this expression up. So the derivative is 4x cubed minus 16x plus 60. So I've got rid of the brackets around the 4. I've done 8 times 2 is 16, so I've got a negative 16. x to the power 1, please don't leave it as x to the power 1. The examiner might not like that. The examiner would like you to show an understanding of the use of indices. So minus 16x and then plus 60 on the end. That's it. That seems to me a fairly generous 3 marks, but there it is. Next, we'll look at part 2. It wants me to show that the x-coordinates of any stationary points of the curve satisfy a certain cubic equation. Okay? Again, if we're on the ball, this will start to link in with part A. So we need to use, again, I suggested this idea of the subject and questions being progressive. This leads directly on from B part 1. Let me write that down again. That was our derivative from part 1. Remember the key 2-word phrase that I highlighted way back up at the start of my presentation in this part 2 of part B of the question is stationary points. You need to show the examiner that you understand that a stationary point is where the derivative is 0. You need to write this down. You need to write down in your presentation of your answer the 2-word phrase stationary points, and you need to write down dy by dx equals 0. Then, as usual, and hopefully you've got the sort of feeling for how I'm presenting these things, don't work across your page, work down your page. The next logical line of working out should go below this one. And that's a general rule in maths. Don't work across your page. That sort of presentation just doesn't work. Okay, so dy by dx equals 0 means, looking at the line previous to that, that this cubic expression must be 0. Is that what they asked for? Well, not quite. But again, provided we haven't made a silly mistake, it's fairly obvious what I need to do to this last line to get what I'm asked for in part 2 of the question there at the top. I need to divide by 4. Dividing by 4, I get exactly the cubic equation that I'm asked to derive. So there was a common factor of 4 in my cubic expression for the derivative there. That's been very carefully worked into the question. Let's move on to part 3. Okay, I've rubbed out part 1 of the question just to give myself enough room. I've left part 2 up so you can refer to that. Part 3 asks us to show that the only stationary point of the curve occurs when x equals -3. So remember, from part 2, and it says use the results above, so I'm going to use my immediately prior result. Stationary points have x values which satisfy this cubic equation. That was the last thing I got at the end of step 4. That was the answer to part 2. Again, it's in the question. It's contained in the question of part 2, just in case you made a mistake up to that point. So from part 3 onwards, if you did not succeed in part 2, you didn't succeed in getting the correct cubic equation, from now on you'd better use the one that the examiner has given you, because whatever other one you've got won't work. Now, again, in the question it said very carefully use the results above. It doesn't quite refer to which result. We've got several results already. So now I have to reach all the way back to part A of the question. And remember that in part A of the question, I factorised exactly that cubic expression on the left there. So I'll remind you what it was. The cubic expression x cubed minus 4x plus 15 factorises in 2 pairs of brackets as x plus 3 times x squared minus 3x plus 5. So you should know this is one way of solving polynomial equations. We factorise them, and the way it works then is whatever's in the first set of brackets here times whatever's in the second set of brackets here is, we're told, 0. It follows logically that one of those brackets, one of the bracketed expressions, must be 0. Write it like this. So either x plus 3 is 0, or x squared minus 3x plus 5 is 0. Some of you might have written and in the middle there. That's not such a big deal. It's not quite correct. I mean, you might like to go away and think about why I've put or there. So let's carry on. I've split my cubic equation into two simpler equations. That's the purpose of factorization. And you'll notice the first one here on the left is linear, and the second one is quadratic. So let's deal with them in turn. The linear one, dead easy to solve. The solution is x equals -3. Next, we need to gird our loins to solve the quadratic equation. Now, it would be quite possible to start out on the wrong path in solving this quadratic equation. That would not be unusual at all, and it'd be absolutely fine. You wouldn't lose marks, but you might end up doing a bit of work which you wouldn't get any marks for. The trick is here to reread that part 3 of the question. They are suggesting that for some reason this equation, the one where I've got ... underneath it, doesn't have any additional solutions. Let's try and match that up with what we know about quadratic equations. The normal way to solve a quadratic equation is to factorize it. So take 30 seconds or so, see if you can factorize in your head that quadratic equation on the right there. You should determine that it's not possible to factorize it. When that happens, we normally think, oh dear, I'm going to have to do something complicated, which means either use the quadratic formula or complete the square. But there's no need to do that. The clue in the question in part 3 above, it's hinting to me that this quadratic equation does not have any solutions. How could I tell that? The standard thing to do is to look at the discriminant of the quadratic equation. The symbol for discriminant is a Greek uppercase letter delta. Looks like a triangle with the apex at the top. Remember, the discriminant of a quadratic expression is b squared minus 4ac. In my case here, b is -3. A is 1, C is 5. So -3 squared minus 4 times 1 times 5. Again, feel free to put that in your calculator. Please, please, please remember the brackets. Otherwise, we're going to mess up even with the calculator. But if we run through that, I'll do it without a calculator. -3 squared is definitely 9. It's positive 9. And then -4 times 1 times 5 is -20. So I'm getting -11. The significance of that is that the discriminant is negative. When you have a quadratic equation in which the discriminant is negative, that means the equation has no solution. So that leaves us with just our one solution, x equals -3. So remember, this equation arose from part 2 when we were trying to identify the stationary points. So we conclude that the only stationary point of the curve occurs when x is -3. Okay, so a bit of work to do there for step 5, for part 3 of the question. And I would suggest 2 marks a little bit mean for that one. But there you go, that's what the examiner's offering us. Let's move on to part 4 of part B. Here again, I think the marking is a little bit generous, this one. It wants me to calculate a value for the second derivative of y with respect to x at that particular value of x. So let's reach back to part 1, where we had the first derivative. You wouldn't necessarily need to write this down again. I'm writing it down again because you can't see it because it's on an earlier slide. To work out the second derivative, we simply differentiate again. So again, I will do this carefully, term by term. Differentiating the first term, 4x cubed, the 4 stays where it is, the 3, the power, comes down in front, and the power decreases by 1. Differentiating a constant times x just throws up the constant, so negative 16 there, and differentiating a constant just gives 0. Let's tidy that up a bit. So I reckon the second derivative is 12x squared minus 16. Look very carefully at what the question is asking me to do. It doesn't just ask me to find the second derivative, it says find the value of the second derivative when x equals negative 3. When you see the word value, sometimes evaluate in a question, the examiner wants a number. At the moment I've got an expression or possibly a function. I need to substitute x equals negative 3 into this expression for the second derivative. So as usual, using brackets, that would give me that. This time I won't insult your intelligence by going through it step by step. I'll just type it into my calculator and I get 92. So that's the value of the second derivative at x equals negative 3. Remember that x equals negative 3 is the value of x where the stationary point for this graph is. I've left the preamble to part B at the very top line of the screen here, so you can remember what we're doing. With these multi-part questions, it's quite easy to forget what we're doing. How does this all connect together? The examiner has a very clear view of how the question all fits together. But let's move on with the final part of part B of the question. It says, hence determine with a reason whether the curve has a maximum point or a minimum point when x equals negative 3. A lot of words there, but only one mark. So this must be a pretty short thing. So remember, what we have found so far, and this is why I've left part 3, question part 3 up on the screen there. We found from part 3 the only stationary point of the curve occurs when x equals negative 3. And from part 4, we discovered that at that value of x, the second derivative is 92. What the examiner is hoping that you are aware of at this point is that what the significance of the value of the second derivative at the stationary point is. The value, 92, is nothing in itself. It's just whether it's positive or negative. 92 is definitely positive. Given that the second derivative at the stationary point is positive, we can conclude that the curve has a minimum point when x is negative 3, so at that stationary point. This is sometimes called the min-pos test. Apologies if you hadn't heard that term before. I do come across quite a few students who claim not to have heard that. Second derivative positive means the stationary point is a minimum point. If the second derivative were negative at the stationary point, then the stationary point would be a maximum point. But that's it. We've worked our way through carefully each of the steps in the question.
Here we can see the function that was in the question. You'll notice that the axes have had to be changed so that we can see the curve nicely. And now if we put a point on the curve and then we can put the tangent to the curve, then if we look at what the value of that slope is, we can put that on the graph as well. So on this line we can put the slope. So we see we have a slope of minus 132. So when we put that value there with a little plus, that's at minus 132. So we have a negative gradient. Now if we move that point round, then this point is going to trace out the graph of the gradient. So we can see that as we slide the point round, the gradient is becoming less negative, or we could say increasing. Then when we get to here, we have a gradient of 0. Right, there we are. And it continues to increase as we go round past the minimum point. Now this point here then represents the second derivative. So that's telling us, as we saw, that the tangent, the value of the tangent was increasing. So if we now slide along the curve, we can see that the tangent line is becoming less negative or increasing. And when we get to 0, it's still in the process of increasing. Now, this is the second derivative, green line, and that's showing that it's not increasing as quickly. You can see that with this slope gradually curving downwards. If we carry on through, then we have this situation. So at the minimum point, the tangent, the first derivative, is 0, but the change of the tangent at that point is that it is increasing, which is shown by the value of the second derivative. So if the second derivative is positive, that tells us the tangent line gradient is increasing, and that tells us we have a minimum. If we turn the whole thing upside down, then we can see what happens at a maximum. So, as we are getting towards the maximum, we have a positive gradient, shown by the tangent line. And then as we slide across, the gradient is decreasing. It's getting shallower and shallower, and as we get to x equals -3, then it is 0. And we can see what's happened again with the derivatives. This is the graph of the first derivative of dy by dx, and it started quite steeply upwards, and it's fallen down to get to 0. The green portion shows the second derivative, so that shows us how the first derivative is changing. And it's difficult to see at this scale, but it is falling, but it's falling a little bit less slowly. You can see it curving round. And if we carry on a bit further, we can see that it decreases less. So, going back to the maximum, we can see that at a maximum, the slope is 0, so the first derivative is 0, but the first derivative, dy by dx, is falling, which means that its slope is negative, which means the second derivative is negative. So if we have a negative second derivative and 0 first derivative, we must have a maximum. When we had a minimum, that meant we had a positive second derivative, so we say min pos. And now we have a maximum with a negative second derivative, so we could say max neg. The important thing is that you understand why the second derivative is as it is for the maximum and the minimum.
Let's review the core skills that we used in this question. It was a very long question broken down to lots of parts, and it may at times seem to have been a little bit tedious, a little bit pointless, but in fact it's a very cleverly constructed question. The examiner has tied together two very important areas of mathematics, and the examiner has tested that you're familiar with various skills relating to these areas of mathematics. Part A of the question is all about the algebra of polynomials. The examiner would like you to show an awareness of the factor theorem and how to use it, and in more detail, the examiner would like to see that you're capable of factorizing polynomials, in this case a cubic polynomial, into a linear and a quadratic factor. And perhaps the other tricky bit in terms of algebra actually cropped up in part B of the question, and that was using the discriminant for quadratic equations. So in this case, you remember we used the fact that the discriminant was negative for that quadratic equation showed us that the equation has no solutions. However, part B of the question isn't actually about principally the algebra of polynomials. Part B of the question is, in fact, on the subject of analysis. Now, analysis as a branch of mathematics, generally speaking, is distinct from algebra. You may or you may not have come across the term analysis before. But in the Unit 1, the pure maths side of the course, Unit 1 and Unit 3, if you like, the various broad areas of pure maths can be broken down into algebra, analysis, and possibly geometry. There is, of course, some overlap between these three areas, but traditionally these are the three areas, the three main areas of pure maths. Analysis, amongst other things, involves dealing with functions. For example, differentiation, also integration, is an aspect of analysis. And in this question, we use differentiation to identify a stationary point and its nature. So again, that's very much part and parcel of analysis, finding out about a function and, in a related way, the graph of that function. Briefly, we'll finish with a look at wider skills associated with this question. One thing we weren't asked to do at the end of the day was to sketch a graph of the quartic function, that's the fourth degree polynomial function that was given to us at the start of part B. Now, in fact, the question was all about that quartic function. Part A was just a preliminary bit of work to help us with a later bit of part B. So go away and have a think about, could you sketch a graph of the quartic function? Do you know what quartic graphs look like in general? As a little hint as to how to sketch a graph of this particular quartic function, see if you can undertake the following task. Can you find a non-stationary point of inflection for this graph? One last thing. Let's finish with algebra again rather than analysis. In step 5, while we were answering part of part B, we got a pair of equations, a linear equation, x plus 3 equals 0, and a quadratic equation. We were able to solve the linear equation very easily, x is negative 3. The quadratic equation, we showed that it doesn't have any solutions. Okay, that's a little bit curious. When you learn a little bit more about some more advanced algebra, you will find a way of expressing solutions to that quadratic equation. It's possible that you already know something about this, but when you come to do the further maths modules, you will learn how to express solutions to that quadratic equation. So if at this stage you think there are definitely no solutions to that equation, there is some excitement, some mathematical excitement ahead for you. To put it into context, let's peg this back. Look at the left-hand equation, x plus 3 equals 0. I'm sure you agree that that has a solution, don't you? We agreed that the solution is x equals negative 3. It may be of interest to you to know that mathematicians of the 15th and 16th century would have said, if you'd asked them to solve the equation on the left there, they would have said, in most cases, that it has no solution. You might like to think about that and why they would give that answer. The way around it, or the way to interpret that, is to perhaps ask a younger and less experienced student, can they solve that equation on the left? And you may have to rephrase the question or rephrase the equation without using algebraic language. Again, back in the 15th, 16th centuries, people did not use this sort of algebraic notation, so it's a little bit of a cheat. But if I were to ask you to solve the equation unknown, when I add 3 to an unknown, I get 0. What is my unknown? some people will say it has no solution. Why is that?